Hello everyone, this chapter is going to cover the X-ray beam for us. There are quite a few objectives, approximately 12. The first objective is describe the construction of the X-ray tube, state the function of each component of the X-ray tube, describe how X-rays are produced, explain the role of the primary exposure factors in determining the quality and also the quantity of X-rays, explain the line focus principle, state how the anode hill effect can be used in radiography, differentiate among the types of filtration and explain their purposes, calculate heat units, recognize how changing generator output, kVp, MA, and filtration affect the X-ray emission spectrum, and list the guidelines followed to extend the life of the X-ray tube. Now we're going to talk a little bit about X-ray production. Bottom line up front, in terms of X-ray production, it occurs when electrons that are moving rapidly from the cathode to the anode are suddenly stopped or slowed down. So decelerated is slowed down, and of course stop, just like you stop your car or stop midstream. Stop means they stop. All right, so inside of the X-ray tube, which we'll learn about, we have a negative electrode, which we call the cathode. When it is heated, electrons are boiled off in a process called thermionic emission. So thermionic emission, definition-wise, that basically just means that electrons are being boiled off of the filament on the cathode side. The electrons, which have a negative charge, are attracted to the anode. All right, the anode of the tube has a positive charge. All right, so just like in real life, how they say opposites attract, the negative electrons that are sitting on the cathode side, which the cathode is negative as well, will be attracted to the positive anode target. All right, once we do apply the kVp as we're taking the X-ray exposure, those electrons which have that negative charge will fly across at high speeds to interact with the anode target. When they interact with the target, again, they are either slowed down or they are stopped. And in the process of being slowed down or stopped, they will create X-rays. All right, we do have two forms of X-rays, which we'll talk about later. The two types of X-rays that are created are either Bremsstrahlung. Those are the ones that are slowed down. Bremsstrahlung or Brems is a German word for braking. All right, if you're braking your car, we're talking about slowing down. And those that are completely stopped are considered to be characteristic type X-rays. All right, now we are going to look at a picture of the X-ray tube housing. So right here, we're just looking at this picture, just really shows us the X-ray tube, but it's actually surrounded by what we call an X-ray tube housing. The housing itself is a protective housing. It is lined with lead, and it does protect the technologist, which is you, the patient, and also the tube. It protects the tube from rough handling. It protects the technologist and the patient from what we consider to be additional X-rays, whether they're off-focused or straight. All right, so in terms of how it shields and absorbs what we call leakage or off-focus radiation, except for that radiation that's allowed to pass through the port window as what we consider the useful beam. Useful beam is that which is going to interact with the patient. All right, there's also, if we're talking about the housing, which is not pictured right here, if you look in your book, you might see a picture of the housing. All right, within the housing or within that insert, it is filled with oil. All right, so the tube itself, which is featured here, is immersed in an oil bath, and that housing and the oil bath provides not only what we consider electrical insulation, it also provides heat protection for the tube. So it helps try to keep the tube cool, and the reason why we need to keep the tube cool is because as we produce X-rays generate a lot of heat. and therefore the more X-rays we take, the tube itself continues to heat up. All right, the only way for it to cool down is for it to sit idle. All right, another purpose of the housing itself is to hold high voltage wires. So again, this particular picture does not show us a picture of the housing, but if you look in your book or just Google a picture of the tube housing, you'll see that there's two receptacle ports at the top, and those ports are where the high voltage wires hook in. All right, those high voltage wires are needed because that is where the electricity is going to come in for us to energize the tube. All right, another thing about the X-ray tube is that it contains fans. All right, fans are used also, just like the oil, to try and keep the tube cool because there's a lot of heat generated within the tube as we create X-rays. All right, one thing to note about X-rays, when they are produced, they are emitted isotropically. So when I mean isotropically, just like when you turn on the light in your home, how the light kind of lights up the entire room, when the X-ray machine is on, for instance, when you're taking exposure, those X-rays emit in all directions. And the only thing that keeps them from going in all directions is the fact that it is enclosed with that lead enclosure. Now, I'm not going to say it keeps it from going in all directions, but it keeps it exiting from all directions because that lead actually blocks the X-rays from getting out with the exception of the leakage radiation. So in this picture right here, you will see the port window that is made a lot thinner than the rest of the unit. So that is the part that is going to allow the X-rays to exit. All right, so that is the only place that we want to allow the X-rays to exit. That is the place where they will exit and interact with the patient. All right, the X-ray tube itself, there's two types of enclosures that it can be enclosed in. We have a glass enclosure called Pyrex or borosilicate glass. If you heard about Pyrex before, it's used in a lot of cooking materials, baking dishes, and the reason for it is because it can withstand high heat. And again, with X-rays, we do produce a lot of heat. And then we also have a metal type of enclosure. All right, both are able to withstand high heat. All right, both enclosures also create a vacuum environment, so it's evacuated of air. There's no air inside, and it encloses what you see right here, which is our X-ray tube. All right, from the X-ray tube that you see right here, you can see that it has a positive electrode or a positive side. The positive side is called the anode, and it also has a negative side, and the negative side is called the cathode. And we'll get a little bit deeper into the other components that you see listed right here. So bottom line, in terms of the X-ray tube protective housing, it's going to be typically made of be lead lined. Inside the X-ray tube itself, it is a glass, Pyrex or borosilicate glass, or metal enclosure. All right, now we're going to move on to the cathode. So we talked about a little bit on the last slide, but the cathode is the negative electrode. All right, the cathode contains the filaments of our X-ray unit. Typically, there are two filaments, so we call it dual focus tubes, and you can see in this image right here that the filaments lie parallel to each other. So generally when we say dual focus, that means two. So here you see that there's two filaments there. All right, the filaments lie inside of or enclosed by the focusing cup. All right, it's enclosed on all sides except for the front that is facing the anode. The focusing cup itself operates on what we call the law of electrostatics. So during thermionic emission, when I say thermionic emission, we're talking about as the tube is being energized, electrons are being boiled off of these filaments. The focusing cup is what actually keeps or repels those electrons back, keeping them tight, even though they kind of want to spread away from each other. Now, why do they want to spread away from each other? So if you go back to high school when you learned about an atom, you learned that it has protons, neutrons, and electrons. So you might remember that electrons are negatively charged. When you think about like charges, if we have a bunch of like charges around each other, like charges repel each other. So with that being said, the electrons have a negative charge, so they're being produced or boiled off. They want to get away from each other, but they are enclosed, with the exception from in the front, they're enclosed by the focusing cup, which also has a negative charge. So as the negatives are trying to get away from each other, they hit the focusing cup, which also have a negative charge. So it pushes them back together. So we call that electrostatic repulsion. The filaments themselves, again, I already said they sit parallel to each other in the focusing cup. They are a coiled piece of wire. The reason why it's coiled, it's not straight, it's coiled to produce or create a lot more surface area. So with that being said, when we press the prep switch, this is something that you probably learn in procedures. You're applying what we consider a current or an amperage to the filament. All right, as we apply that amperage, the filaments get very hot to the point of incandescence. And as it gets hotter, it boils off those electrons that we need for the patient's X-rays. As they're being boiled off, they do sit right there in what we call an electron cloud or a space charge. So I do want you to do it a little bit of research. I want you to define what an electron cloud is per your book or some other resource. Define what a space charge is as well per your book or per another resource. I do want you to look up the law of electrostatics as well as what the definition for thermionic emission is as well. All right, now we're moving on to another part of the X-ray tube itself, and that is the anode. So the anode is the positive electrode. All right, in terms of anodes, there are typically two types of anodes that we have a stationary anode and we also have a rotating anode. They're typically made of tungsten or a mix of several elements. And the mixture of those elements are built not only to withstand the heat that is going to be created due to the bombardment of electrons, it also is built with these materials to have a lot or increase the durability or the life of the tube. Now, the stationary anodes have their, I'll say, limits, so to speak, or disadvantages. Stationary anodes, and we don't have a picture here, so you need to Google. The picture is not here, so just Google what a picture of a stationary anode is. It is basically just a tungsten button embedded in a copper rod. It doesn't move, it sits still, and the electrons are constantly bombarding that one spot. Now, the rotating anode, which you do see right here, it spins and it allows those electrons, they may be bombarding the same spot, but since we're spinning the spot, it does allow the heat to spread out all around the target disk. So instead of a focal spot that we have on the stationary anode, we now have a focal track on the rotating anode. All right, the anode target itself is the part that the electrons are interacting with. So it is responsible for stopping or slowing down those electrons that we need for creating the X-rays that we need for the patient's X-rays. We will eventually see, I think, in this book, or maybe we won't, so I'll just talk about it really quick. To get the anode to rotate, it is rotated by what we call an induction motor. All right, an induction motor is made up of two parts. It's made up of a stator and it is made up of a rotor. The rotor is actually inside of the glass or metal enclosure. The stator is actually outside of the enclosure. The stator, when the tube is energized, there's current that flows into the stator. The stator will have or produce a magnetic field, and that magnetic field is what causes it to become energized, causing the rotor to spin. All right, now we are moving on to target interactions. So when we talk about target interactions, initially when we talked about how X-rays are being produced, so basically we said that X-rays produce when we have filament electrons located on the cathode side. As a result of being heated, they are speeding across to the anode side, and X-rays are produced when those electrons are either stopped or slowed down. All right, so when we say they are stopped or slowed down, we're talking about two types of X-rays or two kinds of X-rays. The two kinds of X-rays that are within your X-ray beam are bremsstrahlung interactions, or we have characteristic type interactions. Now, the majority of your X-ray beam will consist of BREMS type X-rays, so about, I'll say 85% will consist of BREMS type X-rays, all right, produced as a result of the X-rays or electrons being slowed down. The other 15% are what we call characteristic interactions, all right, and they're produced by electrons that are suddenly stopped. So approximately 99% of the kinetic energy from those electrons that are leaving from the cathode interacting with the anode are converted to heat, and approximately 1% will result in X-ray production. Regardless of the type of X-ray production, the interactions will only be 1%. So as you can see, X-ray production is very inefficient. As we are taking the patient's X-rays, about 99% of the electron interactions will produce heat, and only 1% of those interactions will result in X-rays. So as a result, eventually in this chapter, we'll learn about heat units. And also, if you are familiar with X-ray tubes already, you might notice that the housing, as you take X-rays over and over, depending on the volume of your hospital or clinic, the housing itself will get hot. So that is something to be cautious of as you continue to do X-rays that will get hot. And the only thing that really cools it down, we do have the fans, we do have the oil bath, but the only thing that really cools it down is that it sits idle over time. All right, now we're moving on to target interactions. So here we're showing you the target interactions, whether they're bremsstrahlung in nature or whether they are characteristic in nature. All right, so the one on the left is bremsstrahlung. All right, Brem's radiation is produced when we have a projectile electron. So we're talking about an electron that's leaving the cathode, interacting with the anode. Once it reaches the anode or an atom of the anode, it's either slowed down as it interacts with that positive nucleus. All right, remember the electron itself is negative. The nucleus, if you go back to I don't recall if this is maybe physics, the nucleus has those protons in there. So we know that the protons have a positive charge. So with that being said, now we have a negative electron and a positive nucleus. So as you know, opposites attract. So the nucleus pulls on that electron, causing it to slow down. All right, once it causes it to slow down, it will also change directions, and it will leave in a different direction. All right, so it will leave with less energy that it entered with, but in a different direction. Now, when it does slow down, we already know that energy cannot be created nor destroyed, so that loss of energy produces a bremsstrahlung type X-ray. Now, the figure on the right shows you what a characteristic interaction looks like. So characteristic interactions are produced when those electrons that are leaving the cathode interacting with our anode target. They have enough energy when they go in to actually interact with an inner shell electron. Usually the K shell is the innermost shell. It has enough energy to eject it from the atom. As a result of it being ejected, it leaves a vacancy. So that now means that the atom is unstable. To get back down to the stable state, the atom itself will start what they call a characteristic cascade. So we have outer shell electrons now will drop in to fill the vacancy, all right, in a cascade. All right, so when the K shell is vacant, the L shell electron will drop in to fill the vacancy. Now we have an L shell vacancy. All right, to fill the L shell vacancy, the next shell that is beside that one is the M shell. So the M shell will drop in to fill the L shell vacancy. And that process will continue until all of the inner shells are filled. Now, in terms of an atom, when atoms are, I'll say, built, we already know that all the inner shells need to be filled. Outer shells do not have to be filled, meaning they don't need to have 8 electrons, but all of the inner shells need to be filled. All right, but again, that process of the electrons dropping in to fill the vacancies is what we call a characteristic cascade. All right, and that process will, like I said, continue until all of those inner shells are filled. Now, as a result of those electrons dropping in to fill the vacancy, they will release some energy, and that energy will be called a characteristic radiation, and it will be named for the for the shell that is being filled. So that L shell that L shell electron dropping in to fill the K shell vacancy will create a K characteristic X-ray photon. All right, so again, do a little bit more research to figure out what the characteristic cascade is. Also, do a little bit more research on what bremsstrahlung radiation is. We have two, I'll say, electrons coming in on the bremsstrahlung figure on the left and the right, and that basically is telling us or trying to depict to us, depending on how close that electron gets to the nucleus and how much the nuclear field pulls on it, it can either pull on it a lot, meaning the electron traveled really close to the nucleus and it was really attracted to it, the strength was really great. If it pulls on it a lot, it's going to cause it to slow down and lose a lot more energy than if it traveled farther away from the nucleus. Even though it has a pull, if it traveled farther away from the nucleus, the pull is not as great, so it doesn't give up as much energy when it slows down and changes direction. So if it gets really close, it pulls on it, it loses energy, giving off in a bremsstrahlung type X-ray, but it changes directions greatly. If it pulls on it a little bit, it still causes it to slow down and give off energy in a bremsstrahlung type X-ray photon, but it only changes directions a little bit. All right, now we're moving on to X-ray exposure. So X-ray exposure, there's typically 2 phases of X-ray exposure. I'm not quite sure if you really discussed it in your procedures class, but there is a prep button and there's also an exposure button. All right, so there's a prep phase and an exposure phase, and this slide just kind of breaks down what that is. So when we're prepping the tube, if you have any experience in X-ray, you can either press the prep button on the control panel, but most of us have like a trigger type device, and that means that we are pressing that button halfway down. What happens is when we press that prep button, the rotor is activated. So that means that the rotor starts to spin, all right, on the anode side. On the cathode side, something is also happening, all right? We are now applying amperage to the filament, so they're getting heated. As they're getting heated, the electrons are being boiled off in that process of thermionic emission that we talked about a little bit earlier. Those electrons will sit right there at the cathode, so they're going to gather in a cloud called a space charge. And those negatively charged focusing cup that surrounds the filaments will also surround the electrons, with the exception of that which faces the front. The front is open. So the cloud itself is going to kind of be forced together, back together, because we know the electrons want to get away from each other because they have a negative charge and negatives repel each other. Since they're surrounded by the negative focusing cup of the cathode, that cup kind of pushes them back together so they're not allowed to spread out. Now, the number of electrons that are accumulated right there in the cloud are limited by what we call the space charge effect. So I do want you to do a little bit of research on what the space charge effect is. Basically, there's only a certain number of electrons that are going to be boiled off and sitting right there and available for the patient's exam or X-ray. All right, the second part of what happens during the exposure. So initially we said we've either pressed the prep button or we're holding down our trigger halfway. Now this is the part where we're pressing either the exposure button or we're pressing the trigger all the way down. So what happens on the cathode side of that X-ray tube is those negative electrons now are going to be sent flying across. They'll be attracted to, because now we're putting a positive charge on the anode. So they're going to fly across in a string in order to interact with the anode target. On the anode side, since we said it's now has that positive charge based on the fact that we push the exposure button, it is now the target of interaction for those electrons that are flying across. As they interact with the anode, that is where X-rays will at that point be produced for the patient's exam. X-rays and also heat. 1% will be X-rays, whether it's Brimstrom or whether it's characteristic, and about 99% or 99% will be heat. All right, now we're moving on to what we call the emission spectrum. All right, and as you can see right here, it's made up of two parts. This is the complete emission spectrum, but we can break it down and look at it in just the two parts, which would be, we can look at the discrete emission spectrum, which would be just the characteristic part, or the continuous emission spectrum. So the characteristic part is, or characteristic X-rays are not produced until the KBP meets or exceeds 70 keV. All right, or 69.5 keV is the exact number. So if you're doing any exams where your KVP is not at least 70, there are no characteristic X-ray photons in that beam. Now, Brim's X-rays have a range. So those X-rays can range, or they have energy levels just above 0 up to the max energy of what you set for that particular exam. So let's say you set 75 kVp for that exam. BRIM's X-ray photons will have just above 0 up to 75 kVp. All right, if your kVp was 55, BRIM's X-ray photons will be produced in ranges just above 0 up to 55 kVp. So again, this is just a basic picture of the general form of the X-ray emission spectrum. That spectrum again can be divided into characteristic and BRIMS. All right, BRIMS X-rays, if we're looking at them separately, are considered to be the continuous emission spectrum, and those X-ray photons can have an energy level up to the max of the kVp that you set for that patient's exam. And the characteristic or the discrete emission spectrum will have only specific values. So there are approximately 15 different levels depending on which book you look at. So do a little bit of research to look at these emission spectrum separately, the whole emission spectrum together like we see here, and then there's some books that will show you what the Bremsstrahlung or continuous spectrum looks like by itself, and then what the characteristic spectrum looks like by itself. So when I say there's 15 different energy levels involved in the discrete emission spectrum, we're really only concerned about the 5 that occur as a result of the K shell electron being knocked out, and that cascade of LMNO, etc., dropping in to fill those vacancies. All of the other levels, LMNOP, those levels and the interactions that happen as a result of those cascade are not high enough to be effective at producing X-rays. At best, they're going to be absorbed within the patient. They're not going to be strong enough to get out and be useful in producing the image for us. All right, now we are moving on to X-ray beam quality. All right, so I'll say these are terms, so to speak. Beam quality itself is the strength of the X-ray beam or the penetrating power of the X-ray beam. It is controlled by a kVp, so it's telling us, is the beam going to be strong enough to penetrate the anatomy of interest? All right, it does control the shades of gray or the contrast within our image. Beam quality is the number of X-rays that are in the primary beam. So the more X-ray photons that are in the primary beam, the more dense or more dark the X-ray will be, especially if those X-rays are able to penetrate the patient and get out and interact with our image receptor. All right, in addition to these terms, or kVp and which are controlled by kVp and MA, there are some other things that can dictate how many electrons are going to penetrate with our image receptor. All right, so we already said that MA or mass controls it. We can also look at it as just MA by itself. We can look at kVp by itself, and we can also look at time. All of these things will have an effect on the quantity, which affects the density or the darkness of our image, and also whether or not that image is going to be diagnostic in quality or not. They also can affect the patient dose as well, but we're not focused on patient dose right here. Now, on this slide, it doesn't really show it, but some other factors that can, I'll say, affect beam quality and quantity. Quantity-wise, kVp affects it, MA affects it, exposure times affect it, and then other things such as your SID or distance can affect it, your collimation can affect it, and filtration can affect it. Filtration is something that's inherent or built in to our X-ray tubes. Also, it can be added. Filtration is required by law. And what it does is, if you think about a coffee filter, it filters out what we consider bad. So all of those low energy photons that wouldn't even be able to penetrate the patient, it tries to filter out some of those before they are even able to exit and interact with the patient. Quantitative means, or quantitative, the only thing that really affects, I'm sorry, not quantitative, qualitative. The only thing that really affects the quality is going to be the KVP. All right, so now we're just looking at KVP by itself. And as you can see right here, we talked about it just a little bit. KVP is basically whether or not the X-rays will have the strength to be able to penetrate the patient. All right, it not only determines the speed of the electrons that are in the X-ray beam, it also controls whether or not it's going to be able to penetrate. So it says right here, determines the speed of the electrons in the tube current, so in the X-ray beam. The greater speed results in greater quantity and quality of the primary beam. So the higher the KVP, the more electrons and the stronger the electrons will be in terms of being available for that patient's exposure. And increasing KVP will increase the ability of that beam to be able to penetrate the patient's part. All right, next is MA. All right, so MA is a measure of tube current or amperage. It also controls how many electrons will be available in the beam. All right, it says MA is directly proportional to the number of X-rays produced. So as your MA increases, the number of X-rays produced will increase. So if we double the MA, we double the number of electrons that are in the X-ray beam. If we cut it in half, then we cut the number of X-ray photons in half that will be available in the beam for X-ray production. All right, now we can sandwich MA and time together. We call that mass. So beam intensity itself is the amount of energy of X-rays that are going to reach the image receptor. So just like how you increase the MA increases the number of photons, it has that direct relationship. The same thing happens with time, or when MA and time are together. The length of time that X-ray beam is on, so the length of time that the tube produces X-ray, and we look at this in seconds, the more X-rays will be produced, so to speak. So short exposures, we do like short exposures for the most part. And the reason for short exposures is because it helps control motion. I don't know if you really talked about this in your procedures class, because of course your patients did not move in the simulator. But if your patient moves in the simulator, just like in real life, when you take an image of someone with your camera, if they're moving, it can create a blur. So short exposure times help us because it hopefully will ensure that we can get the X-ray done fast enough and timely enough so that the patient doesn't move during our exam, especially when we're talking about children. We really like short exposures. Now again, just like MA, mass, and time, if we're looking at it separately, they all have a direct relationship to the intensity of the X-ray beam. So basically we're talking about the amount of X-rays that will eventually be able to reach the image receptor. In terms of patient dose, as MA or time increase, your patient's dose will also increase. if MA in time is decreased or cut in half, the patient's dose will be decreased or cut in half as well. All right, now here is our calculation or mathematical formula for calculating mass. All right, and it's basically just MA times time. MA times time equals the mass. All right, so time is usually, we're looking at it in seconds, but in the event that it was given to you in milliseconds, which some math problems will, you need to calculate or convert your milliseconds into seconds first before you multiply it by the MA. All right, so these are pretty straightforward calculations right here. I do challenge you to look for some more examples outside of your book and kind of work with those examples as well. Also look for some that have the time in milliseconds. So if it was given to you in milliseconds, you will need to convert it first to seconds before you work with your calculation. If you calculate it in milliseconds without doing that conversion, your answer will be incorrect. But I assure you that incorrect answer will probably be one of the multiple, if it's a multiple choice, it will probably be available as a distraction for you. So again, it's MA times time, and time, the standard for time is the second. So make sure that the time part is in seconds. All right, now we're moving on to the line focus principle. So the line focus principle allows us to achieve the detail that we need with our small focal spot. So it allows for us to have a large amount of heat dissipation as well. Now the line focus principle was initially incorporated into X-ray target, especially when we had the stationary anode, but here, as you can see, all of our anode targets are angled. So before the invention of that rotating anode, because of the heating effects that were produced when using that small focal spot, this is where that line focus principle came into play. Most anodes today have two target angles, and those two target angles do correspond with the large and small focal spot. They're manufactured that way. It's nothing that we can do to change about our equipment outside of just choosing small focal spot or large focal spot. Some terms that you need to be familiar with in terms of the line focus principle, you need to be familiar with the term effective focal spot. That's the area on the anode that's that is the area that is like as seen from the patient's perspective that's being projected onto the patient and the IR. And then we have the actual focal spot as well. That is the area on the actual anode target where the photons or electrons, X-rays, are actually being emitted from. All right, so visually, I won't even say visually, when we decrease the angle, I'll say visually, when you decrease the angle, it makes the area that will be effective smaller, so to speak, and when you increase the angle, it spreads out the stream, making that focal spot larger. All right, next, a trade-off of that line focus principle is the anode hill effect. So this is something that we can actually use to our advantage if we were imaging a part that has what we call unequal thickness and density. Some of those parts would be the T-spine, the femur, tib fib, maybe forearm, maybe humerus. We don't use it too often these days because digital is able to, I'll say, detect very low energies and very high energies, but back in the day, we could use this. So as a result of that line focus principle, we induce something called the anode hill effect. Smaller anode angles will have larger Hill effect. So by virtue of the construction of our X-ray tubes, um, as you can see right here, when the X-rays are emitted, those that are closest to the cathode side are a lot more intense than those that are on the anode side. Now, why? I guess why would you say? All right, the reason is because on the anode side, those that are on the anode side, they have to travel a lot farther, and some of them actually interact with that target hill. They're either absorbed or made less as a result of interacting with the target hill, so therefore the intensity is less. So again, the anode hill effect, it is something that we need to know, but it's not really a big deal or a big factor when it comes to our digital imaging, which is what you're going to be using. You're going to be using CR, which is getting obsolete, and DR. This was more so a big thing when we were using film screen, which we don't use anymore. All right, in terms of beam filtration, again, I talked about this a little bit earlier, but just like your coffee filter, there's something bad that's going on. And the something bad is there are energy levels that are just above zero up to the max that we set on our control panel for the patient's exam. Some of those X-ray energies that are being emitted are not even strong enough to exit the patient and help us create the image. Therefore, by law, our tubes have filtration. All right, filtration is responsible for hardening our X-ray beam. When the beam is hardened, it means that that filtration is absorbing all of those low energy X-ray photons. And as a result, it's increasing the average energy of your X-ray beam. So it doesn't sound right that it increases the energy, but think of filtration. Clover Learning has a video and it talks about grades. All right, if you had, let's say, four grades in your grade book, and one of the grades was kind of low. Let's say you had a 100, a 100, a 100, and a 25. All right, if you average those grades, that 25 is going to bring your grade down, all right, because it's very low, so low energy X-ray photon. Now, if we filtered out that 25, let's say by dropping that lowest grade, and then we averaged the three that were remaining, that was 100, the overall energy now is increased because we dropped out that lower energy level or that lower grade, and it increases to 100 if we averaged it. So that's the same concept of filtration. We have two types of filtration. We have inherent filtration, that is filtration that is inherent within our X-ray tube, so lives within the tube, and that includes the housing itself as well as the oil bath, etc. And then we also have added filtration. So the inherent filtration is approximately 0.5 millimeters of aluminum or aluminum equivalent. Again, typically consists of the oil bath and the envelope, whether it's glass or metal, and also that glass window of the housing. And then added filtration is something that is added by law. It is outside of the protective housing, usually outside of the tube collimator, lead, and the mirror, all of that. It's added between the collimator and the housing, and it's usually 2 millimeters of aluminum equivalent. So when we add those things up, the 2 millimeters of added plus the 0.5 of inherent, it comes up to a total of 2.5 millimeters of aluminum or aluminum equivalent. So that is the total filtration that our machines are required to have by law. All right, now we're going to talk about compensating filtration. One more thing about the total filtration. I already said that it was the sum of the added and inherent filtration. One of the things that it is responsible for, we're filtering out that low energy X-ray photon or hardening the beam. The reason why we want to do that is we're trying to reduce the patient exposure. There's no need to let the X-ray photons come out if they're not going to be able to assist in producing the patient's image. They would only be absorbed within the patient, therefore increasing the patient dose. All right, we can also have something called compensating filtration. You may or may not see this out in the field. I haven't seen it in many, many years. Back in the day, which I'm talking about like late 90s, when I was at one of our military bases, when I worked there, I saw some wedge filters, but I haven't seen any lately, whether it's when I was in the field as a civilian or whether I was just going to visit a student. I haven't seen too many compensating filters. All right, but compensating filters basically are something that we can add in addition to the required filtration. All right, compensating filters kind of assist with things or parts that are non-uniform in nature. So I say non-uniform in nature, what we say non-uniform anatomy. So here we're looking at the foot and we're also looking at, let's say, the torso of a patient. So the first one that you see on the left is what we call a wedge filter. If you were using the wedge filter, you would place it, the thick part, over the less dense part of the foot, which is the toes, and the thin part over the more dense part of the foot, which is towards the heel area. Back in the days of film screen, when you image the foot, depending on what you wanted to look at, if you wanted to see the toes, you would need to dial in a toe technique. If you wanted to look in the foot, look at the foot or the tarsal bones, you would need to have an actual foot technique. If you didn't and you were looking for toes and you didn't have the toe technique, instead you use the foot technique, the toes would be, the metatarsals would be burned out. So darker than we need them to be, possibly a repeat. So these filters kind of tried to make the thickness of the part appear, so to speak, uniform, because now the X-rays are traveling through something that is more dense and uniform all across. All right, the other one, letter B that you see on the right, that's an example of a trough filter. I've never seen or used a trough filter, but it's good for mediastinum and lung type exams. And again, it compensates for the bone in the center and the lungs on the edges. So again, the bone is thicker than the air-filled lung, so we press, the thinner part is placed over the spine, and the thicker part is placed over the air-filled lungs. There are some other filters that are out there that you could use that you probably may not see, but there are K-edge filters or other layered type filters that you can use. Some of these might be used in radiation therapy. Some of them are typically layered with tin and aluminum. Tin and aluminum and sometimes even copper absorb those characteristic X-ray photons. So again, if you're using those type filters, it will assist in reducing the patient dose as well. All right, now we are moving on to heat unit calculation. So as a technologist, there's certain things you want to do to try to prevent tube failure or extend the tube life. There's some things that are in your control. So some things that you don't want to do is you don't want to make exposures that will overload your tube. So you don't want to hold the rotor switch down unnecessarily and often. You also want to look for warnings or look for unusual noises that your machine makes when you're making exposures. And you also want to learn how to use tube rating charts, whether it's tube rating charts or anode cooling charts. And you also want to learn about heat units. Now, not to say that we go into our work every day and we do some calculations on heat units. In fact, some of the equipment that's available these days actually have a ticker that shows you the heat units that are generated per exam. You'll notice that with each exam, especially if you're doing back-to-back X-rays, those heat units will tick up, and over time, as the machine sits idle, those heat units will gradually come back down to or bottom out at 0 if it sits idly. So again, you have to learn how to calculate heat units. If the tube is overloaded, meaning it gets too hot, again, the smarter equipment is not going to let you do the exposure, but back in the day, it may have allowed you to continue to do exposures. And if you continue to do it over time, then you could potentially damage your equipment. All right, so this is how you calculate heat units right here. The calculation for it is MA times the time. Now keep in mind that sometimes you may get a word problem that's combines MA and time together. So it gives it to you in mass. It doesn't matter. You just use that one number. KVP times your generator factor. Some books call this a correction factor. All right, the number that will be plugged in for correction factor, because sometimes this problem may read as KVP times MA times S times C. Doesn't matter which order it's in, you have to multiply all of the factors together. So it just depends on, what book you're reading and what order they put these in. But in any case, you're multiplying all the factors together. What also matters is whether or not the question is asking you if you did one exposure or you did multiple exposures. And we did or will practice with this problem in class or with this formula in class. Now, for the generator factor or the correction factor, whatever your book tells you, whichever formula it gives you is still the same formula regardless of how it's written. For single phase, the generator factor or the correction factor will be the number 1. For 3-phase 6-pulse units, so this one doesn't break it down to you in 3-phase 6 or 3-phase 12. However, some books break it down into 3-phase 6, 3-phase 12, and also high frequency units. So just keep that in mind as you're studying. Again, this chart doesn't break it down in that way, but what we will practice with in this class is single phase will be 1, 3-phase 6-pulse will be 1.35, 3-phase 12-pulse will be 1.41, and high frequency units will be 1.45. I don't know if I can write on this. Let me see if I can. I can. 3-phase 6-pulse. As I mentioned, we are going to use 1.35. 3-phase 12-pulse. As I mentioned, we are going to use the factor 1.41. And then high frequency units, these are just types of X-ray equipment. As you go from single phase to high frequency, we're talking about more sophisticated, more efficient, and more expensive equipment. And we're going to use 1.45. All right. And as I mentioned, some books will write this particular formula as KVP times MA times time or seconds times C. So it doesn't matter if you see it this way, it doesn't matter what order it is, you just are multiplying the factors together. Another thing is, like I said, you're going to be paying attention to whether or not it's one exposure or multiple exposures. If it's 5 exposures, whatever number of heat units you get for the total, you will multiply it by 5, and we will actually practice with a couple problems in class, but I do suggest that you just Google this. There are worksheets out there that do come with the answers in which you can practice this. But again, it's showing right here these particular correction factors, but there are some books that will give you these other correction factors that I gave you. Keep in mind that when you are working with these numbers, no answer is going to be close enough to try and trick you. If we're talking about A, B, C, D, we're not trying to trick you in any way. I briefly talked about extending X-ray tube life, and this just kind of outlines things that you can do or things that you're responsible for as a technologist to extend the tube life. Again, if you're in a facility and there's only one X-ray room, if your machine breaks down, then of course you are out of commission. You can't see patients. If you happen to be in a facility that has more than one X-ray unit, depending on the volume, it could slow down productivity. But again, you're the first line of defense, and you're the one that's responsible for ensuring that you're operating that equipment, not only in a safe manner, but in a manner that's going to ensure that the life of the tube is extended as much as possible, because X-ray equipment is really expensive. So again, tubes do have warm-up procedures. They're more automated now. So basically, if your tube sits idle for a long period of time, or let's say you're in an ortho facility where the machines are turned off at night, when you come in for the morning, someone will be responsible for tube warm up. So it's basically, it used to be a number of exposures that we took at a certain KVP in mass, but it's more automated now. There may be a selection that says warm up, tube warm up, and then you go through, it steps you through the process of warming up your tube for the day. All right, avoid excessive heat generation. So to do that, one of the things that we don't want to do is that we don't want to hold that rotor button down unnecessarily. Some instances where we get on a rotor is maybe we're trying to x-ray a kid that's really squirmy, or a patient that's really in pain. Sometimes if you're working in a group of 2, someone might be behind the control panel, the other patient might be assisting the patient, and that is a time when we typically use the rotor. Any other time, we don't hold the rotor until they say, go ahead and take it really quick. All right, but that's to help with trying to get the patient's exam done really quickly after they have them set where they need them for that exposure. Use lower MA and longer exposure times. We don't want to use low MAs and longer exposure times often. Times when we want to use longer exposure times, maybe it's a breathing technique that we're interested in. All right, the longer the exposure is on, potentially the more patient dose. So we do want to have or limit the exposure time. So we don't want to use very low or long exposure times, nor do we want to use very high max exposures either. Don't move the tube while energized. All right, when the tube is energized and we're taking the x-ray, we don't want to move the tube. It should already be set in the position that it needs to be. And then we always want to listen for or recognize when the machine is not performing or sounding appropriately. And if we do see these things, especially visually or sound-wise, often we want to call in medical maintenance. If we're not responsible for calling medical maintenance, we're going to alert our supervisor so that they can call in medical maintenance to come and service our tube.